We have studied in module 1 of this unit that EMF can be induced in the conductor if the magnetic flux associated with the conductor changes. This establishes a link between electricity and magnetism. Isn't it fascinating to see that there is a loop with no source attached and current starts to flow simply due to the movement of magnet or change of current in another loop? To a layman, it may seem that we are generating electric energy out of nowhere. This definitely cannot be true, for it would violate the law of conservation of energy. The question that arises are, where do the electrical energy in induced EMF or current come from? As there is no source, there must be some conversion of energy that takes place. Which energy is getting converted into electrical energy? With a source, current flows from positive terminal to negative terminal. Here, in which direction the current will be induced? How can we determine that direction? In this module, we will try to answer the above questions. To understand where do we get the electrical energy in an electromagnetic induction, let us study Lenz's law. In 1834, German physicist Heinrich Friedrich Lenz deduced a rule known as Lenz's law, which gives the direction of induced EMF in a clear and concise fashion. Lenz's law states that the direction of induced current is such that it opposes the change in magnetic flux responsible for its production. That means if the magnetic flux linked with the coil increases, then EMF will be induced in such a direction so as to decrease the magnetic flux, the very cause of induction of EMF. Similarly, if the magnetic flux linked with the coil decreases, then EMF will be induced in such a direction so as to increase the magnetic flux, the very cause of induction of EMF. So, Lenz's law can also be stated as the EMF induced in a coil will be induced in such a way that it opposes the very cause of its production. So, Lenz's law wants all conducting loops to keep the flux through them same. It doesn't like if there is any change and it opposes it. Let us see what will happen if we bring a magnet towards the loop. As I move the north pole of the magnet towards the loop, the flux increases towards left, my left, and the loop doesn't like it. It wants to keep the flux same. So, it will induce current in such a way that the flux due to the induced current is in the right direction. Again, my right. With the right hand rule, we see that current must be in anti-clockwise direction. Another point to observe is that if the field due to the induced current is in the right direction, so this side of the loop must be inducing a north polarity. Take a look at the diagram. So, we conclude that the north pole of the bar magnet moves towards the coil, the magnetic flux through the coil increases. According to Lenz's law, current is induced in the coil in such a direction that it opposes the increase in flux or the very cause of induction. We made a nice conclusion by sincerely following Lenz's law. What happens if I do not want to follow what Lenz says? If induced current in my loop is in the clockwise direction and south pole is induced, then what? In that case, the south pole due to the induced current will face the approaching north pole of the magnet, and there will be attraction between the two unlike poles, and this will become stronger and stronger as the two poles approach each other. The bar magnet will then be attracted towards the coil at an ever increasing acceleration because the flux due to the approaching north pole increases in the left direction and the south pole induced will also increase it in the same direction, attracting it without expending any energy. A gentle push on the magnet will initiate the process and its velocity and kinetic energy will continuously increase without expending any energy. Can we imagine a situation where the bar magnet is rushing towards the coil with no one doing any work on it? The answer would be a big no, as this violates the law of conservation of energy and hence cannot happen. So, we need to follow Lenz's law sincerely. An approaching north pole will induce a north pole in the loop and there will be repulsion between them. We have to apply a mechanical force against the magnetic repulsion and work done by us appears as the induced electrical energy in the loop, thus following the laws of conservation of energy. Similarly, if a north pole is moved away from the loop as the magnetic flux towards the right decreases, the induced current will be in accordance with the right hand rule and in the clockwise direction and a south pole will be induced. So, the loop will try to oppose the cause, that is the receding flux, and will induce current so as to increase the flux. You can take a look at the picture. Similarly, if a south pole approaches the loop will induce a current in such a way that a south polarity is acquired by it, so that the work has to be done against the repulsion, which appears as the electrical energy. If south pole recedes, then a north pole will be induced by the loop, and in order to take the magnet away, we have to do the work against the attractive force. Let us do an experiment to observe the working of Lenz's law. We have taken two pipes of equal length. One is of aluminium and the other one a PVC pipe. We have two magnets with us which we allow to fall through the two pipes simultaneously. What do we observe? We are able to observe that the magnet takes time to come out of the aluminium pipe as compared to the PVC pipe. The question is why? The answer lies in the material of the two pipes. As the magnet passes through the aluminium pipe, the magnetic flux associated with it changes and this induces a current in the pipe. Now, according to the Lenz's law, induced current will be induced in such a way so as to oppose the cause. The cause is falling of the magnet. So, current will be induced in such a way that it will try to stop the magnet from falling. Hence, the magnet comes out slower from the aluminium pipe. A PVC pipe do not conduct electricity and hence when the magnet falls through the pipe, no induced currents are developed across it and hence no slowing down of the magnets take place. This simple experiment shows how the Lenz's law works, but we still do not know in which direction the current will be induced. A very handy tool in finding the direction of the induced current is Fleming's right-hand rule. Fleming's right-hand rule gives us the direction of induced EMF in a conductor moving in a magnetic field. According to the Fleming's right-hand rule, if we stretch the forefinger, central finger and thumb of our right hand mutually perpendicular to each other, such that the forefinger is in the direction of the field, the thumb is in the direction of the motion of the conductor, then the central finger would give the direction of the induced current. We talked about in which direction we can induce the current. Now we will be talking about how can we induce the current. An EMF will be induced in the circuit whenever the magnetic flux linked with the circuit changes. We know that the magnetic flux is given by phi equal to B dot A, where B is the magnetic field and A is the area vector, which will be equal to B A cos theta. So, phi can change by either changing B, A or theta individually or by changing any two or all three of them simultaneously. Therefore, the three methods of inducing EMF are: induced EMF by changing the magnetic field. By changing the magnetic field, we can change the flux. So, EMF is induced. Magnetic field can be changed by relative motion or by changing its magnitude. Induced EMF by changing the orientation of coil and magnetic field. When the coil rotates in the magnetic field, the angle theta changes. The magnetic flux linked with the coil changes and this induces the EMF. This is the basis of AC generator. Induced EMF by changing the area A, that is the motional EMF. If we change the area of the coil, the flux associated with it changes and EMF is induced. To change the area, we can move one wire of the loop through the magnetic field, hence the term motional EMF. Motional EMF arises due to the motion of charges through a magnetic field. Let us see how. In this figure, the conducting rod is moving with a velocity of v in uniform magnetic field B, which is going into the paper. So, the loop area is decreasing or the flux associated with it is decreasing, and according to the Lenz's law, the loop doesn't like it. It wants to keep the flux same. In order to keep the flux same, it will induce a current upon itself such that flux increases in the direction which will be given by the Fleming's right hand rule, that is from P, S, R, Q. So, the direction of the current is in the clockwise direction. It will be interesting to find the direction of the current by direction of flow of charges. Look at the diagram. As the rod is moving, free electrons will be moving in the direction of the rod. The field is perpendicularly inward and the force on the electron is in the direction shown by the thumb. Hence, direction of the current will be in the direction opposite to it, same as shown by the right hand rule. Let us compare the two treatments, that is by changing the magnetic flux and by force experienced by the charges when they are moving in the magnetic field, and see what will be the induced EMF by the two arguments. The expression of motional EMF by changing the magnetic flux by moving the rod. The magnetic flux phi B enclosed by the loop PQRS will be equal to B into A, which is equal to B into L into X. Since X is changing with time, the rate of change of flux is given by EMF E is equal to minus d phi B by dt, which will be equal to minus d over dt of BLX equal to minus BL dx by dt. dx by dt is the velocity. Hence, induced EMF E will be equal to minus BLV. Now let us see the induced EMF in terms of moving charges in the magnetic field. As the rod of length L moved with a velocity of v in uniform magnetic field, each charge within the rod moves with a velocity of v and experiences a force F equal to QVB. Electrons move from Q to P according to the Fleming's left-hand rule. The work done in moving the charge from Q to P is given by work done equal to force into displacement, which will be equal to QVB into L. The induced EMF is given by work done per unit charge. E is equal to W upon Q with a negative sign, which is equal to minus QVBL upon Q. So, EMF E is equal to minus BLV. So, to do two different treatments yield the same result, and that's pretty interesting. To explain the existence of induced EMF or induced current, we must assume that a time-varying magnetic field generates an electric field. Let us see how mechanical and electrical energy are related to each other in motional EMF. Now, induced EMF is given by E equal to minus BLV, where the negative sign is the Lenz's law saying don't change the flux. As we can see in the diagram, all the free charges will be experiencing a force from Q to P, and the induced EMF creates electric field. This electric field E vector will be created in the rod as that is where the motion is. Now, we know that induced EMF is equal to minus E into D, which is equal to minus E into L as charges move in the length L. Also, E is equal to minus BLV. Therefore, minus BLV must be equal to minus of electric field E into L. So, electric field E must be equal to BLV by L, which is equal to BV. So, electric field will be developed in a conductor when it is being moved in a magnetic field, and this will be perpendicular to both the magnetic field and the velocity. This electric field that we have can produce a current. The wire over which the rod moves has a resistance. Let us draw this in the diagram. Now, EMF E is equal to I into R. Also, E is equal to BLV. Therefore, I into R is equal to BLV, and I is equal to BLV by R. Now, this is the current carrying rod and it is moving in the magnetic field. It will experience a force which will be given by F equal to I L cross B, which is equal to I L B sin 90 equal to BIL. This force will be in the direction given by the left-hand rule, which is in the right direction as shown in the figure. So, we have our magnetic field and the current, and there is the force experienced by the moving rod. You can see the diagram, and the force required to keep the rod moving inward must at least be equal to this magnetic force. So, the mechanical force required to keep the rod moving towards the left must be given by F, which is equal to BIL. From the equation 2, we have I to be equal to BLV by R, So, the force to keep the rod moving must be equal to B, and in place of I we have BLV by R into L. So, the force to keep the rod moving is equal to B square V L square by R. The mechanical power will be given by P equal to F into V. P is equal to B square V L square by R into V. So, we have everything squared up, B square V square L square by R. It is this power that we need to put in, and we need to put in the energy constantly to keep the rod moving. Otherwise, the rod would like to stop because the magnetic force is applying the brakes to it. So, we can calculate the electric power given to the resistance R that we had drawn. It will be as follows. The power, electrical power mind you, is equal to I square R, which will be equal to BVL whole square upon R square into R. So, this electrical power which will be given to the resistor is equal to B square V square L square by R. Surprise, surprise! The power that the resistor gets is same as the power given to the system by us when we were pushing the rod. This is in line with the earlier statement regarding the Lenz's law, that we have to apply a mechanical force against the magnetic repulsion, and work done by us appears as the induced electrical energy in the loop. That will be all for the module. Thank you.